Let's begin. So I have your test to give back, so I'll do that back, give that back at the end of class.
Are you talking about the class, like the exam or the quiz?
The exam.
Oh.
Yeah, like the test. The quizzes aren't done, but I decided it's probably more important to have the test graded than the quiz, so I switched focus on that last minute. So anyway, yeah, the actual test that you did on Wednesday. So today, though, we are going to talk about inverse functions. In particular, I want to talk about a method by which we can find the derivatives of inverse functions. That being said, I really want us to focus on pretty much the formula I'm going to derive and how to apply it. I'm going to skip a lot of details here, so it's not very typical, but you will revisit this topic in Talk 2, so I don't think you have to go over it in as much detail now, because in Talk 2 you'll actually revisit it. So even the last time I taught Talk 2, I went into this topic, it quite literally I spent 4 lectures on it in Talk 2. I have videos up for Talk 2, you can actually see that I spent 4 lectures on this topic. We're going to spend 1, really giving you the bare bones, pretty much, here's what you need to know to calculate this on a test. That's pretty much all I want you to know, and I'll only tell you enough to be able to do that, or to have some idea of what it means. But for the most part, I will assume you remember everything, so knowledge of functions will be assumed. We'll skip the pleasantries. So I expect you to know the definition of a function, what a function is, how they work, how they behave, what's the domain, what's the range, what's the codomain, things of that sort. I'm going to just assume you know that. And we are going to move on from there. So let's talk about a couple important definitions. Function f of x is called one-to-one. That's the phrase one-to-one. Or you might see the word injective being used, any of these. So if we have a function, we call it one-to-one if, and I'm going to give you a mathematical way to think about this, but we'll explain in words what this actually means. If the outputs of x and y are the same, it means that the inputs x and y had to have been the same. Okay? This means if we look at 2 outputs and they're the same, they had to have come from the same input. There's another way to say this is that distinct inputs, this is called the contrapositive of the statement, you don't have to know that word. This is the same as saying if your x is not equal to your y. If your inputs aren't the same, then they won't have the same outputs. Right? Whenever a function, distinct inputs go to distinct outputs, we call such a function one-to-one. So, for example, I'm going to draw a mapping diagram. Again, I'm assuming you're familiar with these. So let's say this is the domain of a function. This is the codomain of a function. One-to-one means each guy here gets mapped to a distinct guy over there. Right? That's called a one-to-one function. You might have people that don't get hit. The people who get hit, we say they're in the range of the function. But that's one-to-one, where distinct inputs go to distinct outputs. You can have a function that is not one-to-one. So this is not one-to-one. And basically what this means is you have a situation like this happening. Right? So here we have two different inputs going to the same outputs. So if this is my x and that's my y, this is both f of x and f of y. And apparently the outputs are equal, however the inputs are not equal. That violates this statement. So that is one-to-one, distinct inputs go to distinct outputs. We call such a function one-to-one. And you can verify this via calculations by just making sure this is the same. So, for example, suppose f from the real numbers to the real numbers, this defines the domain and codomain of the function, is defined by f of x equals 2x plus 1. This is one-to-one. Since if I set f of x equals f of y, that's saying 2x plus 1 equals 2y plus 1. Subtracting 1 from both sides and then dividing both sides by 2, I would necessarily have the case that x must be equal to y. Therefore, this function is one-to-one. You will never have two different inputs giving you the same output for this particular function. You can also talk about a non-example. If I think of f going from r to r, where f of x is x squared, is not one-to-one. Since if I assume f of x equals f of y, this would mean that x squared equals y squared. This would mean that your x is either plus or minus y, meaning it's possible to have x not being equivalent to y. A particular counterexample is to show that minus 1 and 1 are both the same, but of course 1 is not equal to minus 1. So I have the outputs are the same, but the inputs are not. Right? So this function is not one-to-one, because both the numbers 1 and minus 1 both map to the output 1. And so it's not a one-to-one function. And you can show this in calculations by showing if you assume the outputs are the same, you don't get that the inputs are the same. So that's a one-to-one function. Or it's called an injection or an injective function or a one-to-one function. There's another important property of functions. This is called the property of being onto or surjective. F of x is called onto or surjective if. Now again, I'm going to sort of state it in the mathematical way you'd want to think about it. We had the symbol already. This means for all. If for all y values in the codomain of f, there is, I could also write the symbol there exists, some x value in the domain of f such that f of x equals y. In other words, another way of saying this is that, i.e., the codomain of f is exactly the same as the range of f. It means that everyone in your codomain is the output of someone in your domain. Meaning, you can talk about onto, your function can behave like that. That is an onto function. You can say not onto means here is someone in the codomain that is not in the range. There is no x value over here that connects to that guy over there. So we can say if someone is missing in the codomain, it is not an onto function. Codomain onto means every single person here is assigned by the function. Is given an assignment. So you don't miss anyone in the codomain, in other words. Example. F of x, if I consider the domain to be all real numbers and the codomain to be all real numbers, then f of x, again, let's say equals 2x plus 1, is onto. Because pick any y in R, which here I'm thinking of the codomain, then it turns out that y over 2 minus 1 is also a real number. So take any real number, divide it by 2, and is in R, and now I'm thinking of the domain. And if you take f of y over 2 minus, I don't think I want to, I think I want to have y, if I take f of this guy, that will give me 2 times this plus 1, that will give me y minus 1 plus 1 equals y. Right? So I can pick this to be my x value, and I can obtain any given y value. Okay. So that's what it means to be onto. If you look at, again, y equals x squared, and I don't want to give the impression that something can't be both one-to-one and onto. You can have any combination. It can be both one-to-one and onto. It can be one-to-one but not onto. It can be not one-to-one but onto, and it can be neither. Functions can fall in any of these categories. But with these two particular functions, this function is both one-to-one and onto, and the x squared function is both not those things. But that's not a general statement. Look at the example here. F of x goes from R to R, where f of x is x squared, it is not onto. Since minus 1 is a real number, this is someone in the codomain. But there is no x in R such that f of x is going to give us minus 1, right? There is no real number that when you square it, it will give you minus 1 as an output. Right? So that means this guy is missing. So if you look at the function f equals x squared, minus 1 is over here, but literally no one picks it. He's very lonely. Goes to the dance, doesn't get to dance with it. So no one's going to pick that guy. This function will miss that guy. In fact, this function will miss every single negative number. Okay, so we say it's not onto because the codomain and the range are not the same. And this is still somewhat of a review. I expect you to have spoken about this in Precalc as well, but I am skipping a lot of details here. Note, functions can be neither one-to-one or onto. One-to-one but not onto, right? So they can come in any variety, onto, but not one-to-one, or they can be both, onto and one-to-one, right? So these two properties have nothing to do with each other. They happen independently, right? It's on a basis, case-by-case basis. Okay, you kind of have to test those two definitions I gave you to determine what properties each function have. Now, there's a special class of functions, these guys, the last group. They're going to be our focus for now, because this is precisely the group of functions that have what we call inverses. No other group class of functions has something that we call an inverse. So let's introduce inverses on the scene here. Definition. If f of x is both 1-to-1 and onto, we call f a bijection, or a bijective function. Right? So that's the noun, that's the adjective way of calling it, or a 1-to-1 correspondence. Okay, so that's the definition. The functions that have both those properties that I just spoke about, they're a very special class of functions. We call them the bijections. So I can say this function is bijective, and when I say that phrase, what I mean, it has both the property of being 1-to-1 and it has the property of being onto. So distinct inputs will go to distinct outputs, and every single person in the codomain will be the image, quote unquote, of someone in the domain. Now, in both Calc 1 and Calc 2, a lot of information is going to be left out about these. The bijective functions are super important. That is an understatement to say. There are so many things that we know about mathematics that we discovered by just figuring out that there exists something called a bijective function and then following the properties of the bijective function. So for example, last time you heard me mention that infinity minus infinity is indeterminate because you don't know which infinity is bigger. Where did the idea that one infinity can be bigger than another come from? Turns out we only know that because of bijective functions. If you want to prove that one infinity is bigger than another, a bijective function is the way you can do it. So there are a lot of things that we know about mathematics that comes directly from our knowledge of bijective functions. These are a super important class of functions. Beyond what I can tell you and beyond what a Calc 1 or Calc student can appreciate. Someone who's a math major goes on to higher level classes, will study bijective functions, and you realize, oh my god, these guys really, they're super important. That being said, one reason why they're important for us is, again, these guys are particularly the ones that have inverses. They are the only kind of functions that have inverses. Okay? No other kind of function will have an inverse. Other functions, they can have inverse in pieces. We can like restrict the function and only care about one little part, and that part can have an inverse. But as a whole, for a function to have an inverse, it has to be both. And so let me define an inverse. Let f of x be a function. We say f is invertible, or f has an inverse if there exists another function g of x such that if under the function x the output, if under the function f the output of x is y, then if I take y as the input of g, the output will be x. And this will actually happen in both directions. G is called the inverse of f, and is denoted f to the minus 1 of x. So that's the notation. It does not mean 1 over f. It's an inconvenient notation, and there are times when we might use a slightly different notation, which we'll talk about. But that is called an inverse. Okay. Now, what you want to note here, and you can think of f as a function with domain A and range B and codomain B. The G would be the opposite. Its domain is B and its codomain is A. And this relationship holds means that what an inverse function does is it undoes whatever the original function did. So note, inverse functions undo their counterparts. Which means, for example, if I have someone here called x, and my f will do something to that x and give me an output called y, the inverse is going to take this and bring you back to that. Right? This is what f inverse is. It reverses a function. So you can have a function applying a rule to give you a bunch of other people. If you go to this side and there exists a rule that would specifically undo that particular function, we call such a function an inverse. So an inverse function undoes the original function. And the thing is, it had to be onto because if there was a y out here that this function never outputted, you couldn't use that as a domain to get someone over there. As well as, if a single number here, if two different things came to one thing here, if you wanted to reverse that, how would you know who to bring it back to? Right? A function should only have one output for every input. So if it's not one-to-one, you lose that property. So it wouldn't be a function going the other way if it wasn't one-to-one or it wasn't onto. Some remarks. If G is the inverse of f, then the relationship goes the other way. We can think of f is also the inverse of G. So we could write f equals G inverse also, right? So if the inverse relationship works in one direction, it will work in the other direction. That's the first remark. The second remark is the following. If you take f of g of x, the output will be x for all x in the domain of G. And if you take g of f of x, the output will be x. This will work for all x in the domain of f. In other words, inverse functions have this special property. You can start with an input, put it inside g, but if you take that result and put it inside f, it'll give you back the original x. Okay? Here, this x is kind of like the y in this situation. Conversely, if we start with an input x, we do something, f does something to it. If we take that result and put it inside g, g is going to undo it and give you back the original x. So this relationship will hold. So that is f of f inverse of x gives you x for all x in the domain of the inverse, and f inverse of f of x gives you x for all x is in the domain of the function. So we have those two relationships that we'll be able to talk about inverses because they undo each other. Okay. Now we can get to some calculus. The goal is to find the derivative of the inverse function. So you have a function that you care about, that you're studying, and now you want to study its inverse. And perhaps you want to study its inverse on the basis of calculus itself. So you have a function f of x, and you can talk about f of x, you can find its derivative, you can do all sorts of analysis with it. But then you care about, what about you realize that this function can be reversed, and now you want to figure out properties about its reverse, its inverse. So you can go over here to the inverse and be like, well, can we do calculus now? Can we do calculus on the inverse? Right? Can I find derivatives and etc.? And the short answer is yes with a few caveats, but that is our goal. We want to figure out how to do this, and then we're going to do some examples of applying this. And again, this is not going to be as difficult as you might think. And once again, the thing that saves us is the chain rule. So now, note. Let f be invertible. Then, I didn't make the statement that the inverses exist with the bijection. I'll do that after. Let f be invertible, then f inverse exists, and we would be able to write f of f inverse of x equals x. Now what I'm going to do here is we want to differentiate both sides. With respect to x. Now what would that look like? What does the derivative of this look like? This side here. Yeah?
F prime inverse of x times dy inverse, or dy dx inverse of x.
Right, the derivative of the inside. Let's call it f inverse prime of x. Okay. Equals, what's the derivative of the right side? It's just 1. Which means I can solve for this guy, which is actually the guy I care about, the derivative of the inverse. And we obtain this function. Provided it exists. Of course, there will be issues if this number happens to be 0, then we can say the derivative of the inverse does not exist at that point. Or it could possibly be that maybe the derivative of f prime is not defined at the inverse point, and then it won't exist at that point. But assuming that both of these things work out fine, that would be the form that gives us the derivative of the inverse. So if you know about a function f that you care about, you can find the derivative of its inverse function by applying that formula. 1 over f prime evaluated at the inverse of x. Let's actually now do some examples of applying this formula. By the way, let's put... We're skipping a lot, but let's be somewhat comprehensive here. Forgot to mention. there's a theorem. So this is something that you would have to prove that says if f is a function, then f inverse exists, meaning f is invertible if and only if f is bijective. So if you know it has an inverse, it means it's one-to-one and onto. And if you know it's one-to-one and onto, it means you know there's an inverse. It will go in both ways. And this also said, because the arrow goes in both ways, it means that if either one of these is false, then the other one is false. So if you know the inverse doesn't exist, it means your function is either not one-to-one or it's not onto. And if you know if your function is not one-to-one or not onto, then the inverse does not exist. Any questions so far? So pretty much this is the only new thing I've said. Pretty much everything else you should have known from Precalc. Might take a little bit to jog your memory, but yeah. Let's actually compute some examples. So the first two examples are the ones I really care about. The other one is just for you to see another application. And basically I want you to compute the derivatives here. What if we have the function sine inverse of x? This is sometimes called arcsin. So the sine inverse function, or what if we have tan inverse of x? This is called arctan. How do you find the derivative of that function? Now there are derivatives for all the inverse trig functions, but in Calc 1 I only care about these two. In Calc 2 you'll look at all 6 of them. So the third example is just for you to see another application here. And let me get the specific problem out. Let's say you know y is equal to x to the 5th minus x cubed plus 2x. I want you to find the derivative of the inverse function evaluated at the point 2. So it turns out this function does have an inverse, and I want you to, assuming you could find such an inverse, find the derivative when when the input is 2. And that function will show you some of the challenges we face in answering a question like that, and why that formula is pretty useful. But the first two is just my excuse to derive these two formulas for you, because I want you to know these. Okay, so I'll start it off. I will ask you guys for some help when we get to a certain sticking point, see what you remember. Let's do A. So here our y equals, say f of x, is sine inverse of x. Then we know that the derivative of sine inverse of x is going to be what? Well, let me say something first. If our f of x is sine inverse, this means what is the original f?
Sine.
The inverse.
Oh.
So it would be the sine function, right? Now, of course, the domain is restricted. Hopefully you remember that. Because sine in its entirety doesn't have an inverse. But if you restrict it between minus part of 2 and part of 2, it does. And so, assuming our x falls into that range, the inverse of this guy would be that. And so now, if I wanted to find the derivative of sine inverse, this would be 1 over f prime of f inverse of x. I think I wanted to do it the other way. It's not going to matter, but the notation is nicer, I think. Let's think of the f as the sine and find its inverse. It's the same idea, but the notation would be nicer. Set f of x equals the sine. We want the derivative of f inverse. Right? That's the point. That's what we want. By the above formula, the derivative of f inverse is going to be 1 over f prime of f inverse. Here, that is 1 over. Now, what is f prime if my f is sine? Cosine. So that's cosine of. So it's 1 over f prime of the inverse function, but what is the inverse function if I have sine? Well, that's sine inverse. So it turns out that the derivative of sine inverse is equivalent to that expression. But we actually like to rewrite that without trig functions. And so now the question is, what is that? And this is where you guys can help me. If you were to rewrite cosine of sine inverse without trig functions, how would you do it? That's a Precalc question there. Evaluate cosine of sine inverse of x. You guys remember what you would do here? Does it seem familiar at least? Like, does this look like something you would have done in Precalc? Because I'm pretty sure people do this in Precalc. These Precalcs changed since I was a kid, but I'm pretty sure they do this. So the trick for this would be to do something like the following. You set sine inverse to be some angle, right? Because you're plugging angles into a cosine, which means that your sine inverse is just some angle, right? The sine function takes an angle as the input, it outputs a real number, so the inverse function is going to take that real number and output an angle. So sine inverse of x should be some angle. It should be an angle such that if I take the sine of theta, the result is x. In particular, the result is x over 1. Does that help? What would you be able to say about theta? Sine theta is x over 1. How do you define sine? Yeah? Right, you'll think of that as the opposite over the hypotenuse of some right triangle. This means there is some triangle where that's a right angle, this is a theta, and this would be the opposite, that would be the hypotenuse. You can use Pythagoras' theorem to find the other side. It's going to be 1 minus x squared. Right? So just setting the sine inverse to be an angle, you can rewrite it in terms of sine. Interpret sine as opposite over a hypotenuse, SOHCAHTOA. And then that could construct this guy. Now from this guy, you can actually find cosine of theta. Now cosine of theta would be adjacent over hypotenuse. So that's just 1 minus x squared, right? But my theta was the sine inverse, right? So that means cosine of the sine inverse is that expression. And then we can come back here and we can simply plug that in. So this gives us 1 over the radical of 1 minus x squared. And that gives us the formula here. So another formula that we just know now, the derivative of sine inverse is 1 over the square root of 1 minus x squared. It's a very common function to need to find the derivative of. And of course it doesn't work everywhere. It will only work if your x is between. And again, to really understand the ranges and domain for the x, you have to remember some details about inverse trig functions. But here, you'll notice between plus and minus 1. It'll only work in that short range. So we can derive that formula. Deriving for tangent is very similar. So B, if f of x equals the tangent function, this means we want the derivative of the inverse, but the derivative of f inverse is just 1 over f prime of f inverse. The derivative of tangent is what? Secant squared of tan inverse. Similarly, you're going to set tan inverse equal to an angle and figure out what that would result in. So if we set tan inverse equals theta, this means that theta is equal to tan inverse of x equals theta. This means theta is equal. This means x is equal to tangent theta. Think of that as x over 1. That is opposite over adjacent, which means if I were to draw a triangle in this case, that would be opposite, that would be adjacent, and Pythagoras' theorem would give us 1 plus x squared here. This would mean that the secant of tan inverse is just the secant of theta. Secant is 1 over cosine, so this would be cosine is adjacent over hypotenuse, so we actually want hypotenuse over adjacent. So this is going to be the square root of 1 plus x squared, which means if I take secant squared of that guy, that's just the square of this guy. And then I can come back and plug it in here. 1 over 1 plus x squared. Now we can state that as a new formula. The derivative of the tangent inverse function is 1 over 1 plus x squared. And that actually works for all x. Right, the tan inverse function is actually defined for all x's, and we can find its derivative at any point along the curve. We'll pick up with the next example. I'll give you some more example to do. These you should be able to do with what I just told you. Also try. So next time we'll finish part C in the last example and then go through these four. These guys should be able to do right away. You can probably wait to do example C next class. I think we're not quite out of time. We have 2 minutes, but I'll just use those 2 minutes to hand back the test. One thing about the tests. Just write this down. Not counting the bonus. You got less than 70 on test 1. Set up an appointment with me. Mandatory. You got a 72, but 5 of those points were bonus. That means without the bonus, you got a 68, 67. You should see me, okay? Once you get less than a 70 on the test, ignoring the bonus part, you need to talk to me. Email me, set up an appointment. That being said, let me start to... I mean, the performance here was average. I even had a few people getting over 100, so there are a few people who are in trouble here, and you guys need to talk to me.